Assured interview series in which we are talking about the future of security in next-generation smart connectivity systems comprising heterogeneous IoT and other types of cyber-physical systems. I'm Claudia Santos from Martel, and I'm here today to learn more about Assured, a Horizon 2020 project dedicated to safeguarding the operational assurance of IoT systems. With me today is Ahmad Atamli from NVIDIA, one of the Assured project partners. Ahmad and his team are looking into one of the biggest challenges of building such mechanisms, the efficient monitoring of the behavior of a system that Assured wants to test and secure. Welcome, Ahmad. I'm glad you could join us today to shed more light on Assured.
Thank you, Claudia. I'm glad to be here today with you.
Okay, let's proceed to the questions. In Assured, the use of trusted computing, including trusted execution environments and trusted platform modules, is a core building block. Could you explain what are the core properties offered by these technologies for enhancing security?
Yes, absolutely. The core problem that we are facing today is answering the question is, can I trust this person? Can I trust this device? And why might it seems easy question to answer? It's really not, especially when you're talking about digital devices. We need to define what is trust and what is trusted. How do we define if I can trust something? And to answer this question, there are the theory of what we call trusted computing that has been developed for years now, for more than 2 decades now, which defined what is trusted and what is the concept of trust that kind of help me decide if something is to be trusted or not to be trusted. So we say in this context, we say that something is trusted if it's always behave in the same manner, always for giving input, always give that specific output. So no matter what happens to it, it's always assured that it's have a trusted output that I'm one familiar with, and second, that it's expected from me. There's not going to be a surprise in what is going to give me. It's not going to malfunction in a way that I'm not familiar with. I know exactly what is going to be the outcome, and that basically can help me decide if this thing is trusted or not. But now, in order to answer this question from implementation point of view and from the technology point of view, how should it go about that? The devices need to incorporate some mechanism that will allow them to prove to someone else that they have the right security primitives in place, that they are running the right firmware, they're running the right software, they are having the right configurations. And this way, it will help me decide if I can go further and work with this digital device, and if I want to give it my data, and if I want to kind of get some functionality from it. And it's very important to having this question answered whether I can trust it or not, because a lot of fatal event can happen if a device malfunction or if it doesn't give me the right result that I'm expecting to, and it can be a matter of life and death in many cases, especially when we're talking about IoT devices and embedded devices and critical systems. So to that extent, today the components that are being used and very well known in trusted computing are things like trusted platform model. Trusted platform model can be hardware or a soft device or firmware device, but referred to mostly today, and what we're aiming for is using a hardware, because we tend to trust the hardware more than we trust the software, because we say it's hardwired, it cannot be changed, and thus it's trusted. If something can be changed, it can affect its behavior, we say it's not as trusted. And trusted platform model are cryptographic models. It incorporates some mechanism to provide me this trust guaranteed. And kind of like it stores also the sensitive material and cryptographic material that help me guarantee trust and establish trust with other components. So that's one technology. There's another technology that we call trusted execution environment. And trusted execution environment, a bit of a wider notion that would allow me basically to run the software that is guaranteed that if I want to run specific software, let's say somewhere else in another country, it's guaranteed that it's my software that is going to be running there. There's no other software that can run. and nobody can tamper with that execution. And if anybody tamper with that execution, I will know about it because the result will be different. And this is two technologies that we aim to use in order to enhance the security and our trust with the digital devices.
Okay. And in this context, could you elaborate on what attestation is and how it translates into the trustworthiness of a single device and also the entire supply chain?
The issue that we are facing today is the fact that we have many devices spread all over the world, right? You have Internet of Things. Literally, we are connecting everything to the internet, including your table, your fridge, and your refrigerator, right? And the issue is there are many things like that that we rely on in our day-to-day life. But what really guarantees at the end of the day that this device was not compromised, that I don't have some sort of a cyber criminal that came connected to this device because it has some sort of physical access and it changed completely the firmware. It completely changed the software that is running there. And what I'm thinking that I'm communicating to pay for, let's say, for parking, it's actually a software that is going to just take my credit card and leak it somewhere else for someone to use it. Right? This is a simple example. And it's a very easy thing to do. And it's an attack that is very plausible and possible to happen, especially if you have a physical access to the device. You have physical access to the device. There are no limits to what you can do, and including compromising it and impersonating. And in this context, we really need to guarantee that if we are communicating with a device that's susceptible to compromise, we want to make sure that it's in a good state. We need to make sure that it's in a good state before we provide some private information, before we provide some sensitive data, otherwise we're doomed. And the trust here basically where it comes in place, and there are pre-built aspects that need to happen before basically you get to a point where the device starts communicating with me in order to kind of prove for me that it's trusted. And this is a process of attestation where you have an attestee and a tester. In that case, you are the attestee, you are trying to prove to me that you are in a good state. And if you manage to prove to me that you are in good state, we're going to run a protocol between us where I say, okay, you have this, you have that, and give me this, and I will give you that. And if we manage to run that protocol and you answer the right answers through using the right primitives that you have within the chip, like using a cryptographic aspect that is baked in the hardware, and you manage to prove to me, this is basically where I'm the attester. I say, the attestee is trusted, and I'm now from that point on, I'm going to work with you. And the way this happened is basically we are built all on top of cryptography, because the attester, right, the one who's going to prove to me that he's trusted and I can work with him, is going to have to prove it to me through cryptography that is only possible by that hardware, by that device, and nobody else in the world can go and do the same thing, because this kind of proof can only be generated through some sort of cryptographic mean by that specific hardware device. And this is very, very powerful tool and enabler for better and secure infrastructure, because today, one of the biggest problems that we have is we have hundreds of millions of devices, I would say. It's actually estimated that by 2030, people will have at least 100 IoT devices per person. So there is really going to be an explosion of the number of devices out there. And there's all sort of attack that happen, especially one that happens through the supply chain. You know, before, let's say you are buying a new phone and that it's in transit before it gets to you, someone managed to get to this phone and install some sort of a dodgy software and firmware. And now you're thinking you're getting this great device, but in fact, everything that you are feeding this device is now just leaking it outside, or like ending up spying on you. And with attestation, we basically can start questioning the trustworthiness of that device and can help us if we want to establish any connection with that device and giving it information.
Mm-hmm. And are there any consumer devices that we might know of that are protected by such technologies? And what are the challenges in remote attestation?
Today, there are a few devices on the market, I would say, yes, that do provide this guarantee, starting from Windows 8. I think TPMs already were embedded in these laptops and desktop. Today, mostly every desktop device, mostly you will find a TPM, actually TPM 2.0, which is the latest spec. And through this, you can basically implement your own solution about how to attest a device and if you can trust it or not. Even today, the current ecosystem and the software like the UEFI or the Windows, they are making use of TPM to kind of help facilitate this process of establishing trust. So we do have it exist today in the market. And the challenge, though, become a thing when we're starting to look at lower embedded devices. So low embedded devices are constrained devices. In many cases, we don't have even the place where we can put a TPM chip. There is no place where we can put that. But sometimes it's budget-wise that it's not worth it for us as paying another $2 to put a TPM chips on a device that is very small. So the feasibility of things might not be present in all devices, but definitely present in many of the devices today, especially laptops, desktops, and server. And that allow remote attestation, because with the remote attestation, let's say with servers, you could have literally your own machine that is sitting somewhere else in the cloud, and you can use remote attestation. You can establish a protocol that I just mentioned before, where I say, if you are the one who claim you are, you need to send me a proof that you are running this specific firmware and software. But then I need to also tackle the aspect of how do I know that this is not being sent and generated from, like 100 years ago? And then when I say I'm challenging you, if you are actually the owner and you actually can prove that you are who you are, then I'm going to give you something. I'm going to give you, let's say, a random number. And I say, do some manipulation in it, sign it, give it back to me. And I see if you actually manage to prove to me that you actually hold that key for this proof, then I will basically be able to trust you, because now it's actually fresh. I gave you something for me. You couldn't have generated this before. And this is the concept behind remote attestation, right? I run the protocol with you. And through this protocol, you prove to me that you are running that specific software, you have the right configuration, and then basically I can work and continue working with you to run my workloads.
And in terms of detection mechanisms that are used in low-power devices, what techniques are used to record data, and how does Assured tackle that challenge?
Yeah, today the detection is a complex thing. Mostly the first line of defense that we aim for when we design devices, we're trying to go for prevention. If we can prevent an attack, why to go for detection? The sad reality is this: security is not perfect, and we can never get to a bulletproof solution that solves every possible problem. If you want a bulletproof solution, just power off your device. That's probably the best answer to it. So you don't really have that luxury of having absolute security. And as a result, we know that we have a blind spot in some of the mechanisms that we have. We are limited in what we could do. And when we basically get to this situation of there's only much we can do with prevention, then we go to the second line of defense. And the second line of defense, where we say, how about we detect the problem? If we try to detect the problem, then we're basically able to stop that attack to progress any further. So this is second line of defense. Now, the issue with detection is that it mostly was designed for laptops, for servers, for desktop machine, because it assumed that it's connected to actually powered devices, not battery powered devices, but actually devices that have no issues with power, not something that is limited in a sense of resources, in a sense of battery. And this is the nature of these things. So we don't have as much detection techniques today that are used in lower power devices, because normally the detection techniques quite heavy. They go actually take some really good chunk of your device. That means if they run, they basically kind of like limit the bandwidth, they consume a lot of power, depends on the frequency, how much it runs, and all that basically kind of like make it much less attractive. Also, kind of like the software stack and the complexity of the system is rather different. In desktop devices, you have hundreds and thousands of threads running in there, if not millions, while low power devices tend to be very single focused. So as a result, the kind of things we aimed for, the community and the security community aimed for, is to tackle this bigger problem in these complex systems. And there wasn't as much available in low power devices. So to that end, as we're seeing more IoT devices being spread all over the world, the attacks vectors are getting more and more, and we're seeing the ability of cyber criminals that are being more able to come up with sophisticated way to attack the system. As I said, physical attacks are within scope, and this becoming also another problem. Software attacks within scope, which is another problem. And there is more interface with the user. And the second we're saying there is more interface with the user, this is when you expose yourself more to attacks. And this is the type of attacks that prevention can't help as much in many of the cases, and you require detection technique. And in Assured, we took a shot at this problem. We said, how about we take a concept that was applied in servers and we try to apply it for low power devices. And what we're doing with Assured, we take this concept of how about we look at a small footprint in the memory. We try to scan the memory of that device periodically in a way that it doesn't affect that implementation and doesn't really require much power beyond what is the device is consumed. And low power devices today are equipped with more sophisticated and more advanced security primitives. So with Assured, for instance, we look at the device, a low power device, as two worlds. We're saying the world that will run the detection solution and will go about scanning that memory. And scanning that memory would allow us to go and build the primitives of the behavior that's happening in the system. And this is two worlds that are living in parallel. So you have the world that basically still serve the user, still connect to the outsider world and interact as it normally does. But then we still have another world that is running at low frequency and only using one core, which is scanning the memory, building the behavior of the system. And once we build that behavior of the system, we constantly generating some sort of proof to someone that is external that the device is in good state. So we are basically this new primitives called a tracer in order to trace the execution and the behavior of the program. And from there, we take it from there and we use it and combine with remote attestation in order to prove to someone else that the device is still not compromised, that the device is still in good state. And this is a very new and powerful thing, because so far, if you remember, we talked about remote attestation, but we didn't talk about how often that happens. And remote attestation happens only once in most cases. People just want to know once you power the device if it's in good state or not. You don't really know if at a later stage the device got compromised or didn't get compromised. While with Assured, we're saying, no, you attested that device, but we don't know, we cannot tell if that device got compromised at a later stage in life. And remote attestation as is today doesn't take you that far. So we combine this with what we call the tracer, which is also basically getting behavior analysis of that specific device, how it's executing, and we combine it with remote attestation to constantly prove to someone remote that we are still in a good state, that you can still trust us, and the system is not compromised.
And is there anything else you would like to add about Assured as we're running out of time?
Yes, thank you for this, Claudia. So Assured, Assured is a really good project in tackling, as I said, the problem of low power devices. To summarize what I said earlier, it takes the concept of trusted computing technologies like trusted execution, like a TPM, like a new concept that are research-based, like a tracer that we developed and researched it, and combine it all together to create new primitives that provide good trustworthiness in the infrastructure. So you can establish a good trusted network, you can establish trust between different devices, and you can improve the resiliency of the system overall. So it's really tackling one of the big challenges today in security.
Well, thank you for that. Thank you for being with us today and shedding more light on Assured.
Thank you.